Now that we have sort of finished analyzing our sort of very basic infinite quantum well, where V is equal to 0 inside and infinite everywhere else, we can start sort of moving on to other sort of more complicated potentials. So the reason why we're actually going to move on is because we've sort of discovered at this point that the square well that we've derived so far is complete, and that we can express any arbitrary wave function big psi of x comma time to sort of be equal to this infinite summation of coefficients c sub n, and going from 1 to infinity multiplied by the sort of separable solutions psi sub n, phi sub n for our infinite square well. So in this way, sort of any arbitrary wave function, including ones that are not for sort of this simple square well, can be decomposed into sort of this summation of separable solutions for the infinite square well. And by doing this, we can automatically sort of find the probability of this big wave function that's more complicated and not necessarily having a potential of 0 being in some energy state E sub 1, E sub 2, E sub 3, etc., etc. And this is useful. However, doing this process sort of requires us to already know what big psi actually is, because remember that sort of the method to find c sub n involves using Fourier's trick, which requires to know what psi is ahead of time. So in the case where we don't know psi ahead of time, we actually have to once again return to the Schrodinger equation and resolve it for whatever sort of potential that we have. So now that we have finished analyzing the most basic one, which is just that V equals 0, we can move on to sort of more complex ones. And we start with the harmonic oscillator, which is sort of the most commonly encountered type of potential that shows up frequently throughout like all fields of physics. So before we actually solve the Schrodinger equation for the harmonic oscillator, let's start by reviewing what a harmonic oscillator actually is. So physically, a harmonic oscillator is traditionally defined as having some sort of wall with a spring attached to some sort of mass, m, and this spring has some spring constant k, such that, and let's also put this on like a frictionless floor so that we don't have to worry about friction, like that. This is the wall, and that's the floor. Both are frictionless. Now, the requirement for being a simple harmonic oscillator is that the force that the spring exerts on this mass has to follow Hooke's law, which is that the force must equal negative k times x, where k is the spring constant, and x is sort of the displacement from the equilibrium position, where the equilibrium position would be the location along sort of this x-axis that m would be on if we sort of didn't initially displace the string and just sort of set it at rest with the spring in neutral. So the corresponding solution that comes about this can be solved just by setting this equal to mass times acceleration via Newton's second law. So this is equal to m times d2x by dx squared. And this is just a very easy differential equation that we can solve. Solving it sort of yields that our general solution for x is equal to some constant a times sine of omega t added with some constant b times cosine of omega t. Where omega is defined as the square root of the spring constant k divided by m. And this, the actual derivation process for finding this is sort of covered intensely in any sort of intermediate or even beginner classical mechanics textbook. So if you aren't familiar with this or feel like you're rusty, I encourage you to sort of go back and read up on the physical, more intuitive version of the harmonic oscillator before we move on to the quantum mechanical version. So the corresponding spring potential energy that comes with this is defined just as V equals 1/2 kx squared And we have to realize that realistically, such a potential system is not possible. We are once again working in the world of idealized systems because, as we've said very early on when we started with the infinite square well, a lot of real-life physical systems are just way too complicated for us to be able to properly model. And in this case, the simple harmonic oscillator is also one. So we model it with this sort of idealized equation, but realistically, this is not perfectly accurate. If we stretch a string, a physical spring, for example, too far, that causes the metal to deform, and Hooke's law also generally doesn't really work after a certain point is reached. So because of that, this is sort of an idealization, and we're going to sort of, once again, look at this ideal system and try to solve it. So next is the reason why we actually even care about simple harmonic oscillators, and the reason why these are important, and we're not looking at some other sort of arbitrary simplified system for our quantum systems, is because the simple harmonic oscillator can be used as a sort of a good enough approximation for a lot of different systems, for any system that has what's called a local minimum for potential. So what we mean is that let's consider some arbitrary system that is not a simple harmonic oscillator. Let's consider some sort of system, let's consider some sort of system where our potential, V sub x and x, and it looks like some crazy thing, like something like this. And this is obviously not a simple harmonic potential, because a simple harmonic potential sort of requires us to have a perfectly parabolic system. So, and let's analyze sort of this local minimum right here, and we'll call this point x comma x naught as sort of a reference to our equilibrium point that we traditionally would use in classical mechanics. And we can sort of mathematically prove that any sort of system can be sort of decomposed into something that is effectively a simple harmonic oscillator, as long as we have this sort of relative or absolute minimum, whichever one you would prefer. So we start by sort of introducing the Taylor series. So any function v sub x that has any arbitrary shape, at any point we can sort of express this v of x function as a Taylor series about some minimum x naught, which we've defined here. So v of x, if expressed as a Taylor series about this minimum x naught, is going to be equal to v of x naught plus v prime of x naught times x minus x naught, and then we add 1/2 times v double prime x naught times x minus x naught squared, and so on and so on and so on for this sort of Taylor series expansion. So if x naught is sort of the location of a minimum, then what we can do is we can start by just defining v of x naught to equal 0, because for any sort of potential, what we care about is not the actual potential itself, but rather the difference in potential. So there's nothing stopping us from just setting our reference potential at v comma x naught equal to 0. If you've taken sort of electrodynamics, then you should be very comfortable with this idea that we can just sort of set the 0 for our potential anywhere, because all that does is offset all the potentials that are everywhere else. And because of the fact that the difference in potential is the only thing we care about, this is sort of arbitrary. So because of that, this automatically we can set to just equal 0. V at x naught is a minimum, so because of that, the derivative v prime x naught is automatically also equal to 0. So we have this final term, 1/2 v double prime of x minus x naught squared, and then a bunch of higher order terms. And we can sort of ignore the higher order terms, because the reason why is because we sort of made the claim that this approximation of analyzing sort of a absolute minimum, or analyzing any sort of minimum as a simple harmonic oscillator, only works for small oscillations. So where x is sort of very close to x naught. So because of that, if x is very close to x naught, then x minus x naught is going to be small. It's going to be a very small value. And if we square it, it's going to get even smaller. If we cube it, it's going to get even smaller, and so on. So we ignore all of the higher order terms and just sort of approximate as 1/2 v double prime x minus x naught squared. Next, sort of, we can recognize that this is effectively just a simple harmonic potential, because if x naught, if we sort of displace our x-axis and define x naught to equal 0, or yeah, x naught to equal 0, and therefore our equilibrium point, then this is effectively the same thing as 1/2 k x squared, because the x squared in this case for the spring potential is the difference, or the distance away from the equilibrium point. So as a result of that, x minus x naught in this top case is also the distance from the equilibrium point, where x naught is our equilibrium point. So if we set x naught, which is our equilibrium point, to just equal 0, then we sort of have the identical system, except that k is actually equal to the second derivative v double prime. So therefore, sort of simple harmonic oscillators are important, because any arbitrary system that has sort of a local minimum can be approximated as simple harmonic, so long as the magnitude of our oscillations are small, aka as we're sort of the distance by which we're going from sort of x minus x naught to x plus x naught is very tiny. So sort of if we're only analyzing motion around this tiny range, then things are approximately harmonic, and because of that we can sort of model a bunch of the behavior of lots of systems where we sort of only displace it by a tiny amount as sort of approximately simply harmonic. So now in quantum mechanics, our goal is then to sort of solve the Schrodinger equation using such a potential where v equals 1/2 kx squared. As it turns out, mathematically it's more convenient to express k using omega instead of k. So in quantum mechanics, the potential of interest that we're going to be dealing with for a simple harmonic system is, instead of 1/2 kx squared, going to be equal to 1/2 m times omega squared x squared. And the reason that we turned k into m omega squared is because we defined this earlier, where omega equals square root of k over m. So for this sort of system, if we plug it into our Schrodinger equation, then once again note that this potential is time independent, which is one of the requirements we made for sort of separable solutions. Since this has no time dependence, sort of if we do separable solutions, then the phi of t time dependent inseparable solution sort of remains unchanged, whereas our x dependent solution sort of becomes negative h bar squared over 2m times the second derivative of little psi, which is our time independent wave function with respect to x squared, plus whatever our potential is, v times little psi, and this is equal to the energy times psi. So now that we know that we're going to set v equal to sort of our harmonic oscillator equation, we can just replace this and say that this is equal to 1/2 m omega squared x squared. Let's add the psi here that I accidentally deleted. All right, and now we have to actually solve this time-independent wave function, and this is significantly, considering the fact that the simple harmonic equation is a relatively sort of simple step up from the infinite square well, the math that we actually need to solve this is significantly more complicated, and there actually turns out to be two different methods we can use to sort of solve this solution. There's an algebraic sort of brute force method that is sort of very unintuitive and requires us to take a bunch of steps that Griffiths sort of gives to us, and we don't necessarily know why he does it. So it's a very good sort of machine. The machinery for the algebraic method is relatively good, and it allows us to sort of mindlessly plug and chug away solutions to actually find what psi is. However, it's very unintuitive, and it doesn't necessarily, it isn't something that we would be able to do without Griffiths sort of egging us on, telling us exactly what to do for each step. The other one is a slightly more intuitive method, and we'll start by going over the algebraic method, because that one is sort of the mindless plug and chug that we can just sort of follow Griffiths' orders and sort of go on and do the machinery and get our solutions by brute force. And then once we actually have an idea of what the solution is supposed to look like, we can use the more intuitive version in order to sort of get some better understanding of the actual process of derivation. As I've sort of said earlier, the algebraic solution sort of is not a particularly intuitive process. It requires us to take a number of steps sort of for granted and to just sort of follow along in Griffiths' path as he sort of trailblazes his way to actually solving this. And most of the steps aren't actually explained. However, it does provide a very nice sort of machine framework for us to mindlessly sort of plug and chug and obtain solutions. So we're going to do this first, and after we finish the algebraic solution, we will use the more intuitive solution to sort of maybe actually get an understanding of what exactly is happening. So we're going to start with the x-dependent separable solution for the Schrödinger wave function, which uses the potential here defined for a simple harmonic oscillator. And the first thing that we're going to do is we're going to redefine everything in terms of operators. So the operator for x sort of still remains as x, but the operator for p, if you remember, is defined such that p hat is equal to negative I h bar times d by dx. Move this down a little bit to make it a little bit nicer. Negative I h bar d by dx. So if we replace everything, then what we're going to get is, well, from here we have a second derivative right here. So p hat squared is going to be this same thing applied twice. Two negatives make a positive, but I times I makes a negative again. So this is going to be negative h bar squared times d2 by dx squared. So if we write everything in terms of operators, we have, let's see, 1 over 2m times p hat squared plus 1/2 m omega squared x squared. And this whole thing is acting on psi, and this equals E times psi. And we're going to distribute out something to make this a little bit neater. We're actually going to end up distributing out 1 over 2m for both terms. We're going to get 1 over 2m on the outside, and then our p hat squared plus, and then the 1/2 comes out. However, the m is going to go from m to m squared because we have 1 over 2m on the left that's getting distributed out. So this becomes m omega x squared. And this whole thing is getting multiplied onto psi, and this equals E psi. And the reason why we're doing this is because we sort of want to relate this to the sort of energy function that we derived earlier based on the Hamiltonian operator, which is that h hat is in fact, whoops, that is a very messy hat. H hat psi is in fact equal to the energy E times psi, this is something that we derived back in 2.1. So if we sort of link these two together, this sort of implies that h hat is therefore equal to 1 over 2m. Make that m a little bit nicer. Times p hat squared plus m omega x squared. So now we have a Hamiltonian operator for our simple harmonic oscillator system in quantum mechanics. And here we're going to sort of take the first step that sort of Griffiths is going to trailblaze for us, that we don't necessarily know why he's doing it this way, but it does lead us to the correct answer. So we will sort of blindly follow this derivation path. So the goal here
in order to actually solve for psi is to take this Hamiltonian function and factorize it. Because if we look at this, if we sort of treat this as one variable u squared, and we sort of treat this as the other variable v squared, then this is just, this can sort of be viewed as sort of u squared plus v squared. And this sort of implies that we can sort of factor this out, because if you've taken sort of complex math before, we know that we can write this as sort of, let's write this in color code actually, because we did this earlier. So this is actually u squared in red. So one of the things that we know about in sort of for complex math is that we can write the following form. So u squared plus v squared is in fact factorable and can be written as imaginary I times u plus v multiplied by negative iu plus v. And we can check this. So this is, let's see, the first term is going to be u squared. And then we have plus iuv. And then we have minus iuv. And then we have plus v squared. So these two middle terms sort of cancel that, and we have u squared plus v squared. So this is a true property as long as sort of u and v are just numbers. Now, the problem with sort of doing this analogy is that here we have operators. We have p hat and we have x. And x itself is an operator. So I suppose we can also write this as just p hat plus m omega x hat squared. So what we have here is that instead of u and v being just random arbitrary numerical variables, we have them instead being sort of operators. So instead of u squared plus v squared, we actually have u hat squared plus v hat squared. So the question that we're going to ask is whether or not this sort of process of factoring u squared plus v squared into this complex term, whether or not this is possible if we were dealing with, instead of sort of numbers in the form of u and me, instead if we were dealing with operators. And the answer to this, as it turns out, is no. And the reason why will become clear very shortly. But for now, let us define two new operators. We'll call them a hat plus minus. So these are going to be sort of the idea of using sort of these sort of multiplications. So let's define, so let's see. Let's say that u corresponds to p hat, and let's say that v corresponds to, no, let's do this color coded. V corresponds to m omega x hat. So this sort of implies that we should be able to decompose it into something that involves multiplying two things. Let's call them a hat plus minus. And this is evidently going to be of the form of something like plus minus I p hat plus m omega x. So we have something like this, and the reason why we're writing this out is because this is basically analogous to sort of this top thing right here. Now, mathematically, as it turns out, it's actually more convenient to sort of write this in a slightly different manner. So we're going to do that. Once again, we're not going to give a reason. The reason is that it makes the final mathematical formula work out slightly neater, but we are going to have to change a few things here. So the first thing we're going to change is that we're going to add a constant at the front. We're going to add a constant of 1 over square root of 2 h bar times m omega. And the second thing we're going to do is we're actually going to switch the order of these. So a plus is going to correspond to a negative I p hat, and a minus is going to correspond to a positive I p hat. And once again, the reason why we're doing this isn't exactly clear. The actual reason is just because this makes the final math a little bit more convenient to work with. It makes the equation a little bit neater. But we don't really have a reason for doing this right now. We're sort of just following Griffiths' trailblaze as he sort of gives us steps that we sort of just blindly follow. And that is sort of going to be what this entire section of doing the algebraic proof is going to be, is just us sort of getting drip-fed steps by Griffiths for no rhyme or reason and seeing everything sort of magically work out at the end. So we've defined sort of a hat plus minus as this in analogy to the idea of u squared plus v squared being able to be written as like a polynomial of iu plus v and negative iu plus v. So let's actually multiply this. So what happens if we multiply a hat minus times a hat plus? So this is going to be equal to, let's see. So we have this factor of 1 over square root of 2h bar m omega at the front. So we have 1 over 2h bar m omega because it's getting multiplied by itself. So the square root goes away. And then we have, since these signs are opposite, we're going to have I p hat plus m omega x multiplied by negative I p hat plus m omega x. So let's multiply this out fully. So once again, the factor at the front just gets brought down without any problems. So let's copy paste this. And then we use distributive property to multiply these two polynomials together. And what do we have? Let's see. I and I, so these two, we have I and negative I. So that's a negative times a negative, that should become positive. So this is p hat squared for the first term. And then what do we have? We have this one times this one. So plus I p hat m omega x. And then what do we have? We have minus m omega x times I p hat. And then plus m omega x squared. And this is sort of where the difference between using operators for something like this versus using normal numbers arise. Because if these were just standard variables, these two terms would automatically cancel. However, for operators, when we have, for example, p hat and x hat instead of p and x, what's actually, and let's actually, just to emphasize that we're working at operators, let's also add the hat onto x as well. And the thing about operators that's unique compared to standard numbers is that they actually generally aren't commutative. And what I mean by that is that p hat times x isn't necessarily the same thing as x hat times p. So what we can do is, to make this a little bit more clear, is we rewrite this with 1 over 2 h bar m omega at the front, as always. And then let's move the first and last term to the left. So we have p hat squared. And then we have plus m omega x hat squared. Let's add the hat here as well. And then what we have is, let's see, we can move the, for convenience, we're gonna distribute out negative I m omega. So negative I m omega, and then we have x hat p hat, which is this term right here, subtracted by p hat x hat, which is, p hat x hat comes from this term right here. And, you know, normally, once again, if they were just normal numbers, if x hat and p hat were just standard numerical variables, this would just automatically equal 0 because we have xp minus px, and because of commutative property, they're effectively the same thing. However, and we're sort of throwing this out without giving any proof, but since apparently, according to Griffiths, operators are generally not commutatable, this is no longer necessarily guaranteed to equal 0. And because of that, we have now this extra term here. And as it turns out, this actually has a name. This is called the commutator. And in general, what happens is that it's written more specifically with brackets. So if we have, for example, two operators, a hat and b hat, the commutator of a hat and b hat is defined as the bracket of a hat comma b hat. And this is going to be equal to a hat b hat minus b hat a hat. And what we're going to find is that it's actually possible to calculate this explicitly. But before that, let's rewrite this in the proper sort of commutator notation. So rewriting a hat minus a hat plus, this is going to be equal to, and everything sort of at the start remains the same. So we have 1 over 2 h bar m omega. We're going to multiply this by p hat squared plus m omega x hat squared. And then let's sort of use distributive property. So we have negative I m omega at the top and 2 h bar m omega at the bottom. So this becomes negative I over 2 h bar. And then the commutator of x hat p hat. And now let's actually solve this, because it is in fact possible to solve this explicitly. So to find what x hat and p hat is, let's actually act on and function with it. So let's act x hat comma p hat onto some arbitrary function f of x. And what this means is that we're going to have to rewrite this. And remember that p hat is equal to negative I h bar d by dx. This is going to be x times negative I times h bar times df by dx. And we're subtracting this by, this time p hat is on the outside, so negative I h bar d by dx of the quantity f times x. So if we use sort of product or product rule, then this is going to be, so we have negative I h bar x times, and I'm just going to write this as f prime, and then plus I h bar, and then let's see, we have f prime x plus f. So automatically, we should see that this first term and this second term cancel, leaving us with the final term, which is just I h bar f. So therefore, as a result, the commutator of x hat comma p hat is just going to be equal to I times h bar. So let's sort of plug this back in to our function. And what we're going to get is, sort of instead of this commutator thing, we write it out explicitly to equal I h bar. So the h bars cancel out, the two i's make a negative, which cancels with this to become a positive. So everything else cancels, and we get 1/2 on this side. So this is plus 1/2. And now realize that we can sort of substitute back in the Hamiltonian into this equation. Because originally we sort of defined the Hamiltonian to equal, let's copy paste this. sort of redefine, we defined the Hamiltonian earlier on to equal this function, and this is exactly what we have right here, is 1 over 2m times this whole thing over here. So we can rewrite this in terms of the Hamiltonian. What we're going to do is we're going to rewrite this as, let's see, the 2m disappears, so we just have h bar times omega at the bottom. This entire term over here just gets absorbed into h hat. So h hat. And then we're adding on that extra 1/2 term right here. Now, we can rearrange this a bit, and we can rewrite this in terms of the Hamiltonian. So we start by moving the 1/2. So this goes down to here, and we're going to subtract the 1/2. And everything then gets multiplied by h hat omega, or h bar omega, and this equals the Hamiltonian operator h hat.
Another sort of really important thing that I want to note is that the order in which we multiply a hat minus and a hat plus sort of matters, because we originally sort of stated that in general sort of operators don't necessarily commute, and since a hat minus and a hat plus are both made up of operators, they are themselves also operators. So here we defined h hat in terms of the product a hat minus a hat plus. We can do a simultaneous, sort of an analogous sort of derivation, which involves taking a hat plus times a hat minus, and the result will not be the same. So as it turns out, I'm not going to sort of waste my time doing this, because it's the exact same step we did here, but we just multiply a hat plus times a hat minus instead of a hat minus times a hat plus. And what will happen is that if we isolate h again, what we'll get is that in terms of the product of a hat plus times a hat minus instead of a hat minus times a hat plus, the Hamiltonian operator can be written as a hat plus times a hat minus, and instead of minus 1/2, it's going to be plus 1/2. And this whole thing, once again, multiplied by h hat, or h bar times omega. So there's the difference here is that apparently these two are equal. This sort of implies that this term is equal to this term. And this means that a hat minus a hat plus is equal to a hat plus times a hat minus plus 1. So we can write this as a commutator relationship, because if we move this over onto this side, then what we're going to get is that a hat minus times a hat plus minus a hat plus times a hat minus is equal to 1. Therefore, the commutator of a hat minus comma a hat plus is actually just equal to 1. Finally, now that we've written all of this out, the last thing that we're going to do is we're going to rewrite the Schrödinger equation in terms of the Hamiltonian, but this time substituting the Hamiltonian with these a hat operators. So originally we had that h hat times psi is equal to e times psi, and now we've sort of realized that h hat is equal to either a hat minus a hat plus minus 1/2 h bar omega, or if we switch the order around, a hat plus a hat minus plus 1/2 h bar omega. So we want to, let's write both of these down. So evidently this is going to be equal. So the h bar omega comes down as normal. And then we have, if it's plus minus and plus or minus plus minus. So let's do a hat to include both of these. We do a hat plus minus times a hat minus plus, and then plus minus again, 1/2. Psi is in fact equal to e times psi. So we've done a whole lot of work in order to convert sort of the original Hamiltonian Schrödinger expression into this thing, which uses this weird a hat operator. So it still isn't exactly clear how this actually helps us solve the problem, and Schrodinger has sort of been not Schrodinger. Griffith has sort of been leading us by the nose this entire time, and not really telling us the purpose of why we're doing this. But the actual proof for solving the wave function psi is going to be done finally by sort of claiming this final property. And this property is that given some psi, and actually I'm going to copy and paste this in because it's a rather important part of this proof. This is the proof. So given that we have some psi that satisfies our harmonic oscillator Schrodinger equation with energy E, then acting this a hat plus operator on psi will satisfy the equation again, but this time with an energy of the original energy E, but added with a constant h hat omega. So to prove this mathematically, what we're going to do is we're going to write h hat. So we have h hat psi equals E psi. So let's see what happens if we do h hat of a hat plus times psi. And what will happen here is that if we substitute the equivalent for h hat, which is, remember right here, we solved for both of these, we're going to plug in this right identity here. And once again, the reason why is that it'll make the math work, as opposed to if we plugged in the left one. There's not really any other reason other than that this one is what makes the math work out. But once again, this is a very led by the nose, plug and chug blindly without asking questions sort of proof. So that's just what we're going to do. So let's copy paste this down here. So we know that h hat is equal to this property. So this is evidently going to be equal to, let's see, h bar times omega times a hat plus times a hat minus plus 1/2 multiplied by a hat plus times psi. And what we can do is we can actually absorb this a hat over here into our parentheses. But remember that order does matter. Order matters very much for when we're doing with operators. So we have to add this a hat plus to the right of both of these expressions. So let's do that, because since the order matters, so this is going to give us h hat omega multiplied by a hat plus a hat minus as before, and with our additional a hat plus absorbed into it, plus 1/2 a hat plus times psi. And now we can once again take advantage of distributive property, this time taking everything on the left and moving it out to the left. So if we do that, this is going to give us h bar omega a hat plus, and now that the left side of both terms is one less, we have a hat minus times a hat plus 1/2 times psi. And now what we're actually going to do is we're going to move this out again, because these are just constants, so it doesn't matter what happens to the constants. Constants will commute perfectly fine. And we're going to do a hat plus, we're going to move the a hat plus out to the left, and it's going to act on this entire thing, h bar omega times this whole expression right here. And finally, we can note that a hat minus a hat plus is the commutator relation between this and the original, which is that, I'm going to write this, I'm going to copy, whoops, that's not what I wanted. I'm going to copy this and move it down here for reference. So we're going to note finally that a hat minus times a hat plus is actually equal to a hat plus times a hat minus plus 1. And if we write this out, then this is going to give us that this is equal to a hat plus times h bar omega times a hat plus a hat minus, and then we have 1 plus 1/2. and this whole thing gets multiplied by psi. Well, psi should not be outside of the integral. It should be inside. I mean, not the integral, the parentheses. So that's my mistake. This whole thing is multiplied by psi, and then we close off the brackets like this. And finally, we can recognize that this sort of term here is just h hat time plus h bar omega, because we defined h hat earlier up here with the left identity, or this identity right here, that this is equal to a hat plus a hat minus plus 1/2, and we have a hat plus a hat minus plus 1/2, so this is actually equal to a hat plus times h bar omega of h hat plus 1 times psi, where all I've done is I've taken this a hat plus a hat minus plus 1/2 and I've turned it into h bar, or h hat, big H hat, the Hamiltonian operator, because we defined that earlier here, right here, as h hat equaling a hat plus a hat minus plus 1/2. And now that we've done this, we can distribute back outwards the h bar omega, and this is going to give us apologies, I just realized I made a mistake here. The h hat bar omega gets absorbed into the h hat, so this is actually just h hat, and then added with h bar omega. Like that. Because we have h bar omega, yeah, because our definition requires us to have this extra h bar omega multiplied on the right. And so we have now sort of this property. So this is evidently now equal to, let's see, this is going to be equal to a hat plus h hat plus h bar omega times psi. And we already know that h hat times psi is going to give us E, so this just automatically becomes E. And then this whole thing right here is a constant, sort of this entire term right here. So it commutes perfectly fine with our operator, so we can move the operator onto the other side. So this actually equals E plus h bar omega times a hat plus times psi. And thus we've sort of proven this expression. So originally we started with h hat times a hat plus psi, and we end up with the energy E plus h bar omega times a hat plus times psi. So we have proven that given that psi is a solution that corresponds to energy E, then a hat plus times psi is a solution that corresponds with E plus h bar omega. And as it turns out, if we do a exactly identical process, but instead this time use a hat minus instead, then we'll get that the a hat minus expression is going to be equal to E subtracted by h bar omega times a hat minus times psi. So what this is implying is that if we can find one solution for our quantum harmonic oscillator, then we can use these operators that these operators actually have a name, these a hat plus and a hat minus. They're called ladder operators, and we can use these ladder operators to generate additional solutions with new energy values. So now the question is, how exactly do we actually find psi itself? Because we still don't have a way of finding psi. We have a way of generating new solutions given a psi that we already know, but we don't actually know how to find psi itself. And the secret to sort of solving for psi is to recognize that a hat minus is lowering the energy by some constant h hat or h bar omega. And the implication of that is that there's going to be some sort of minimum energy that we can't go under, because E must be equal to either 0 or some positive value. It doesn't make sense for us to have negative energy. So because of that, there's this sort of implication that evidently there's some psi, we're going to call it the ground state wave function, psi naught, such that a hat minus times psi naught must equal something that is not sort of physically realizable. And there's two ways for a wave function to be physically non-realizable, because back in chapter 1 we discussed the idea of how Schrodinger's equation actually allows for physically impossible wave functions because they can't be normalized. So there's two ways for a wave function to not be normalizable. The first way is that its integral over all of space from negative infinity to positive infinity equals infinity. And the second method, or the second sort of process, is that it equals 0, or that the wave function itself equals 0, because then its integral over infinity would also equal 0. And realistically, for this case, the one we want is that this must equal 0. So if this equals 0, so the ground state is the lowest possible energy, and this means that lowering it again is not possible, which implies that lowering it again must give us some wave function that is not physically realizable, and therefore must equal 0 in order to not be normalizable. We then write this out fully, because we already have sort of the formula for a hat minus, and we write this out as 1 over the square root of 2 h bar times m omega, which we sort of defined earlier, multiplied by h bar times d by dx plus m omega x, plus m times omega x times psi naught equals 0. And let me just make sure that my definition is correct. Yes, my a hat plus minus is minus plus I hat p, then yeah, okay, yeah, this is correct. Okay, so we've written out a hat minus to equal this thing as the per definition. Now let's distribute this out fully. So first off, since this is equal to 0 on the right, then this constant at the front just goes out to 0. So we have that, let's see, d psi naught by dx is equal to negative m omega over h bar times x psi naught, where we just took distributive property and then moved everything to either the left or the right. So this is a relatively trivial integral to solve. We can just do an integral of psi naught prime over psi times dx, and this is going to equal integral of negative m omega over h bar times x dx. The first term goes to ln of psi naught, and this is going to equal negative m omega over 2 h bar x squared, and we're going to add the integration constant at the right. Solving this by exponentiation, this is just going to say that psi naught equals the constant at the front, which is going to be, we're going to turn c into an a, is going to be equal to e times negative m omega over 2 h bar times x squared. And further on, we can also normalize a by taking the integral, so magnitude of a squared times the integral of e to the, let's see, negative m omega x squared over h bar dx must equal 1. So we just take the integral, do this into this is a relatively trivial integral anyway, and this is going to give us that sort of the magnitude of a squared has to equal 1.
Let's write this out for clarity, that this integral goes from negative infinity to infinity. Okay, so yeah, so this is a Gaussian integral. To actually do this, you can plug it into a calculator, or you can actually do it via the method of Gaussian integrals. I'm a little bit too lazy to sort of go through the process for that because it's a rather lengthy derivation. So I'm just going to write out the answer, and the resulting answer is that magnitude a squared has to equal 1. So magnitude a squared does not equal 1. That's my mistake. It equals, I think, the square root of m omega over pi h bar. And this I'm just going to get by plugging this into an integral calculator. But if you want to actually solve this, you need to know how to do a Gaussian integral, which the wiki provides a relatively good derivation for how to do Gaussian integrals. You could look there if you want. But in that case, psi naught, therefore, plugging a back in, is going to equal m omega over pi h bar, this time to the 1/4 instead of to the 1/2. And then we have at the front this exponential e to the negative m omega over 2h bar times x squared. And next, to determine sort of the corresponding baseline energy, we can sort of shove this back into Schrodinger's equation, because the Schrodinger's equation in terms of the ladder operators, as we've defined earlier, is h bar times omega times a hat plus times a hat minus plus 1/2 times psi naught, and this equals the baseline energy, E naught psi naught. So if we sort of exploit the fact that psi naught is already sort of a ground state energy, so realize that sort of operators have to act in order. So a hat minus has to act on psi naught first, and that's automatically going to give us 0, and a hat plus acting on 0 is just going to be 0 again. What this means is that this term just goes to nothing. So now we have h bar omega, or 1/2 h bar omega psi naught equals E naught times psi naught. So we cancel out the psi naughts, and therefore the baseline energy E naught is equal to 1/2 times h bar times omega. And therefore, we have sort of managed to solve the quantum harmonic oscillator algebraically. I'll bet we took many steps from Griffiths that we sort of ourselves we probably would have never I don't know what the past term for think is. Basically, we took a bunch of steps from Griffiths that we ourselves would have never thought to do, because a lot of these things are pretty esoteric. A lot of, like, the introduction of ladder operators and whatnot. It's a very good machine, and it lets us sort of find solutions always, because we can just mindlessly plug and chug according to this method, but we don't really know why exactly he did this method. So we're going to do some examples for sort of this general method, and we're going to do some problems, and then we'll move on to the more sort of intuitive method that sort of allows us to maybe get a better idea of what actually is happening during this derivation.